Okay. All right. Okay, thanks. One announcement, fourth milestone, right? Fourth milestone is due on Monday next week. That means you have 1 week, 1 week for fourth milestone. And this one is going to be most difficult, difficult problem in this class project. So major hurdle, right? So I'd like you to start as soon as you can. Good news is once you finish fourth milestone, the fifth and the last one is going to be super easy. So first one is major problem. Okay. And today's class and class on Wednesday, we will talk about this the issue in fourth milestone. Okay. Okay, let's get started. So pipelining, okay, pipelining. So far we discussed about single cycle CPU design, right? No pipelining, but now pipelining. This one, Yunsu, can you please?
Can you hear me?
Yes.
Processor performance. Performance of single cycle processor is limited by the long critical path delay. The critical path limits the operating clock frequency. Can we do better? New semiconductor technology will reduce the critical path delay by manufacturing with small-sized transistors. Can we increase the processor performance with a different microarchitecture? Yes, pipelining.
Okay, thanks. The single cycle CPU, think about single cycle CPU. It is, good in a sense that it is very easy to understand, simple and very easy to understand. But the problem with the single cycle CPU is it is suffering from very long critical path delay, meaning that performance is the problem, right? You cannot increase the performance, clock frequency, right? Because the path, the delay is pretty long. So we want to use, in industry, no one is using single cycle CPU design. Okay. So then, how to increase the performance? Two options. First one, you can use new semiconductor technology. Okay. So new semiconductor means new transistor, small transistor. Transistor is what? Transistor is basic unit of building digital logic, right? Using a transistor, you can create AND gate, OR gate, flip-flops. Using those logic gate, you can create what? ALU, multiplexer, decoder, and so on. Then by combining these components, you can create something wonderful like CPU, right? So the transistor is again the basic unit of building digital logic. So then new semiconductor technology means what? You can reduce the size of transistor. You can use a small sized transistor. Small sized transistor means what? So let me draw cross section of very classic transistor, the cross section. So you have gate and cross section, right? Source and drain, source and drain. Okay. By applying some voltage here in gate, 0 volt or 5 volt, you want to control this switch. Okay. Sometimes you turn off the switch, sometimes you turn on. If you apply 0 volt to this gate, then electricity is passing through, current is flowing between these two. Sorry, 0, then you cut off, okay? You apply 5 volt, then current is flowing between these two. But if you apply 0 volt, then no current, switch is off. A new semiconductor technology means this one, channel length. This one is called channel. So electricity is passing through, this channel, right? The channel length is getting smaller and smaller, right? If the channel length is small, then time to travel from this this place to drain, source to drain, right? The path is shorter, right? Path is shorter, then it takes shorter time to travel, right? So new semiconductor technology, this number, 65, that is the number, right? 65 nanometer, okay? What is nano? 10 to the power of -9, right? And first generation Core i7 is using 45. So 65 to 45 nanometer, okay? Then fifth generation, 14 nanometer technology, 14. And these days, industry is using 7 nanometer technology, 7 nanometer. That got reduced. So this channel length is getting smaller and smaller. Right? Then electricity, current can go through from source to drain pretty quick. Right? So the delay is going to be shorter. So delay is going to be shorter, then critical path delay is also getting shorter. So that means you can increase the performance. But this option, we are not that interested in this option. Okay? New semiconductor technology, right? That is, the people in electronics engineering department, they are interested in this new technology. They are building a transistor, right? Electrical engineering, electronics engineering, material scientists, they are creating this new transistor. So, second option, we are interested in this second option. We want to use a different microarchitecture. So we as computer architects, we want to use different CPU structure to enhance the performance, right? And most classic and obvious, very intuitive way of enhancing performance is adopting this pipelining. It's very intuitive. Remember this one? This analogy. Okay, washer, the laundry example. So sequential laundry, right? Washing step, dryer, and folding, right? Single cycle, sequential laundry, single cycle CPU. Whereas pipelining, right? Pipelining, as soon as N is done with this washer, Brian goes next immediately, right? You don't have to wait. Brian doesn't have to wait until N is done. N is done everything, right? So that is the pipelining, very intuitive, right? Minju, can you please? Q1, can you please? This one.
Pipelining doesn't help latency response time of a single task. Pipelining helps throughput of entire workload, multiple tasks operating simultaneously. Unbalanced lengths of pipeline stages reduce speedup. Potential speedup equals number of pipeline stages.
Right. So, we went through this PowerPoint slide. So pipelining is not helping with latency, right? The latency is what? From the beginning to the end of this single task, right? Still 90 minutes from beginning to the end. But pipelining is dramatically increasing throughput, right? What is throughput? How many tasks, how many laundries can be done within certain amount of time. So in this case, each hour you can process 1.14 laundries, right? And if you apply pipelining, multiple tasks are running at the same time. So if you look at this timeline, 40 minutes, washer, dryer, folder, these 3 hardware resources are being utilized at the same time, right? Simultaneously. If you move to next time slot, okay, 40 minutes, same thing, right? Washer, dryer, folder, are utilized at the same time. Next 40 minutes, same thing. Next 40 minutes, continuously, right? And the key message is unbalanced length of pipeline reduce the speed up. And potential speed up is equal to number of pipeline stages. So this one is a 3-stage pipeline. You have to go through three different steps: washer, dryer, folder, right? So if the pipeline is balanced, meaning each stage is taking same amount of time, right? Washer, 30 minutes. Assume that it is taking 30 minutes, dryer, 30 minutes, folder, taking 30 minutes, balanced. Each stage is taking same amount of time. If the pipeline is balanced, potential speed up is equal to 3 times faster than sequential laundry, right? So how come? In the sequential laundry case, every 90 minutes, right? Every 90 minutes, one task is done. But if you apply pipelining, every 30 minutes, right? Every 90 minutes versus 30 minutes. Every 30 minutes, next 30 minutes, next 30 minutes, one task is done, right? So 3. So potential speed up is equal to number of pipeline stages. We have 3-stage pipeline, so 3, right? But if the pipeline is not balanced, okay, so that is the example. This one is an example. 30 minutes, 40 minutes, 20 minutes, right? Pipeline is not balanced. That will reduce the speed up because this is the bad guy, right? Dryer is the bad guy. It's taking 40 minutes, right? So every 40 minutes, one task is done, right? Instead, 30 minutes, right? So that means speed up is, in that case, sequential laundry 90 minutes versus 40. That is opposite. Sorry. So 90 minutes, 30 minutes, 90 minutes, 40 minutes. Okay. So that is the speed up, right? 2.25, right? 2.25. 2.25. Okay, that is the message of pipelining. And we want to apply the technique in CPU design. So we want to improve performance by applying pipelining. And pipelining will dramatically increase the throughput. Okay, so this is the one. Sequential execution, single cycle CPU, okay, and pipeline CPU. So in this case, we assume CPU execution is each instruction should go through 5 different stages like this. First one, instruction fetch. Second, decoding, right? Register file access. Next one is ALU operation, essentially execution stage. ALU operation, right? And fourth stage is data access. Okay, data memory access in case of memory access instruction. Okay, so you want to use that stage. And the last one is register file update. Okay, register file update. So let's assume 5-stage pipeline: fetch, decoding, execution, memory access, write back. Okay, so, and if you draw pipeline execution diagram, this one, pipeline execution diagram, right? Then it works like this, right? If you take a look at this timeline, right? CPU is processing these 3 instructions, 3 memory access instructions, and ALU is computing memory location for first load instruction, right? X0 plus 10, X0 plus 100. And register file is providing source operand for you, right? Source operand for second load word instruction. And instruction patch unit is reading new instruction that happens to be memory LW instruction. That means these three hardware resources are being utilized at the same time, right? So if you draw, so let me draw clock here. So if you draw a clock in this pipeline execution diagram, it looks like this. Single sequential, execution case. Clock is running like this. Single cycle CPU, right? Each instruction need one clock cycle for execution. Single cycle, right? This instruction gets executed in this clock, and second instruction got executed in second clock cycle, and so on. Single cycle CPU, right? Whereas here, clock is running like this, much faster. Okay, like this. Okay. So we will talk about this. Okay. So you have to keep this in mind, right? This clock is running much faster. Okay, much faster in pipeline CPU case. Okay, let's move on. Okay, this one. Dongwoo, can you please?
Can you hear me?
Mhm.
Multiple instructions are being executed simultaneously. Pipeline speed up. If all stages are balanced, meaning that each stage takes the same amount of time. Time to execute an instruction is time to execute an instruction divided by a number of stages. If not balanced, speed up is less. Speed up comes from increased throughput, which is the latency of instruction.
Okay, thanks.
Does not decrease.
Okay, thanks. The same message as that laundry example, right? So if you apply pipelining, it dramatically increases performance. And in this case, every 2 nanosecond. So if that pattern goes on, right? If instruction stream is infinite, CPU execute infinite number of instructions like this, then every 2 nanosecond, this 2 nanosecond, first instruction is done, right? Next 2 nanosecond, second instruction is finished. Next 2 nanosecond, third instruction is done, and so on. Okay, compare that against a sequential single cycle CPU. Every 8 nanosecond, right? Every 8 nanosecond, one instruction is done. Next 8 nanosecond, second instruction is done, and so on. Okay, then pipeline. The beauty of pipelining, right? So look at this timeline. These 5 different hardware resources are being utilized at the same time, okay? Inside the CPU, right? Register file is updated, okay, for first instruction, and memory access stage is reading data from this location, 0 plus 200, okay, and then ALU is computing memory location, which is 300, 0 plus 300, right? And register file is also preparing some operand for false instruction, whatever it is, right? It is preparing source operand. And instruction patch unit is reading new instruction. Okay, so that means these 5 different hardware resources are being utilized. That pattern goes on and on, right, forever, right? So here, 5 different resources utilized. Next 2 nanosecond, same thing. Next 2 nanosecond, 2 nanosecond, same thing. right? Very efficient. Hardware is very efficiently utilized. Okay, so this one. Okay, Yeonjae, can you please? Okay, Sujin, can you please? And Sujin?
Can you hear me?
Mm.
RISC 32I ISA is designed with pipelining in mind. All instructions are 32-bit 4 bytes. Compared with x86, CISC 1 to 70-byte instruction. Regular instruction format can decode and read register in one cycle. Low store addressing. Calculate address insert stage, access memory info stage, alignment of memory operand in memory. Memory access takes only one cycle. For example, 32-bit data word is aligned at word address.
Okay, thanks. A little bit confusing message from this slide, but the thing is RISC-V architect designed RB32I instructions with pipelining in mind. So instructions are very simple and regular. So it is very easy to apply the pipelining technique. That is the message. Okay. So don't worry about detail. The thing is RISC-V instructions are very simple and regular. Okay. So you can apply pipelining very easy. Okay. Okay, that is the one. Okay, we want to use a 5-stage pipeline. Okay, and 5-stage pipeline is composed of instruction fetch and decoding, and here execution. Okay, execution, you have ALU and memory access stage. Then the last one is write back stage. Okay, write back stage, register file is updated. Okay, here you are using register file. Decoding stage also you are using register file. But decoding stage, you are reading from register file, right? Operand preparation, reading, right? Operand source operand preparation from register file. But in write back stage, you are updating this write operation. You are updating register file. Okay. We want to use five-stage pipeline, and 5-stage, 5 in 5 stages is very classic and classic number, and also very natural number, and also very intuitive number. Actually, 5-stage pipeline. Okay. So then the question is, what do you have to do? What do you have to do? Create pipelining in CPU. So you want to insert this bar, right? You want to split this hardware, this piece of hardware, and this piece of hardware, and this one, this one, this one. So how to insert this vertical, bar? Okay. So what do you think? How to insert bar? Simple. You cut the line. You cut the line, this one, and insert flip-flop. Okay. You cut this line, cut this line, cut this line, insert flip-flops. Okay. Cut this line, insert 1, 2, 3 flip-flops. One flip here, same thing. 1 and 2 flip-flops. So cut the line and insert flip-flop. So it is this simple, right? Pipelining is realized by inserting flip-flop. Okay. Okay. This one. Yunshik, can you please? 지상, 한지상.
Shading indicates the unit is being used by the instruction. Shading on the right half of the register file or memory means the element is being read in the stage. Shading on the left half means the element is being written in that stage.
Okay, from now on, let's use this convention for explanation purpose. Okay, so shade on the right. Shade on the right means the unit is being you are doing read operation. Okay, again, shade on the right, shade on the right. Then you are doing read operation. Look at this, LW instruction, right? Instruction patch. So instruction memory is being read. You are reading, right? Reading from instruction memory to get instruction, read operation. Shade on the right. So you are reading from register file, source operand preparation, right? Shade on the right, read operation. Okay, here. Shade on the right, LW instruction, meaning LW, right? You want to read from some memory location, right? You want to read the data from this memory location. So shade on the right, read operation. And here, shade on the left. That means we want to do, you are doing write operation, update operation, shade on the left, right? So right backstage, shade on the left. You are updating what? Updating register file. So shade on the left. And full shade means you are fully utilizing hardware resource. That means ALU, for example, right? In execution stage, you have ALU. ALU is doing this data addition operation. So let's use the convention. Okay, this is a timeline, and then shade on the right and left. Okay. Okay, this one 성필, can you please? Okay, 상혁, 고상혁. 윤유상.
Others,
Mhm.
it would be happy if we split the data path into stages and the CPU works just fine. But things are not that simple as you may expect. There are hazards. Hazard is a situation that prevents starting the next instruction in the next cycle. Structure hazards. Conflict over the use of a resource at the same time. Data hazard. Data is not ready for the subsequent dependent instruction. Control hazard. Fetching the next instruction depends on the previous branch outcome.
Okay, thanks. So, pipelining is created by inserting flip-flop, right? So if you insert flip-flop and create pipeline, CPU works fine, then we are happy, right? But things is not that, that simple, right? So if you just insert flip-flop, that will introduce new problem, okay, which is called hazard. And there are 3 kinds of hazard: structural, data, and control. Let's go over one by one, okay? And fourth milestone is about data hazard detection and resolution. Okay, that is about, fourth milestone is about this data hazard. And the 5th milestone is about this control hazard. Okay, so we will focus on data hazard today and Wednesday's class. Okay, so but let's go over one by one. First, structural hazard. Structural hazard is very simple. Hijin. Okay, 지원, 설지원. Okay, 승민, can you please?
Structural hazard is a conflict over the use of a resource at the same time. Suppose the RISC-V CPU with one connection, one port to memory. Load or store requires data access in memory stage. Instruction fetch requires instructions access from the same memory. Instruction fetch would have to be stalled for that cycle, would cause a pipeline bubble. Hence, pipeline data paths require either separate ports to memory or separate memories for instruction and data.
Okay, thanks. Structural hazard is very simple. Conflict over the use of hardware resource at the same time. Thing is, one hardware resource, two guys are trying to access one hardware component at the same time. Then that is structural hazard. Let's assume we have one connection. We have one connection, right? One pair of connections. One pair means address and data. Okay, one pair of connections between CPU and memory. Okay, then let's with this configuration, let's draw pipeline execution diagram with this example. So look at this. 4 instructions, right? You want to execute these 4 instructions, and that is pipeline execution diagram. Okay, so fetch, decoding, execution, mem, write back, and same thing, right? Fetch, decoding, execution, mem, write back. Right. The problem is, if you look at this, time slot 6 to 8. Okay, 6 to 8. Memory LW instruction. LW instruction need to access memory, right, to read the data, right? And instruction fetch unit is also need to access a memory to read new instruction. But the problem is we have only one connection, right? We assumed CPU, memory, one pair of connections, right? So that is address line and data. Okay? So one guy can use this pair of connections one at a time, right? So we have memory access unit and we have instruction fetch unit. That time slot, if you look at this time slot, these two guys are trying to use that connection to access this memory. So structural hazard, right? Two guys are trying to access one hardware component at the same time. That cannot be done, right? So in our class project, we don't have structural hazard because we have two separate connections, two pairs of connections like this. Okay, first connection is for instruction fetch, and second connection, first connection is for instruction fetch, and second connection is for accessing memory. So we don't have a structural hazard problem. Okay. By the way, structural hazard is very simple problem. One hardware resource, two guys are accessing, two or more guys are trying to access one hardware component at the same time. Okay. So we don't have structural hazard problem. So to resolve that problem, you have to either provide separate port like this, not this one. You have to provide separate port, the first port and second port, two separate ports, or separate memory, two different memories, right? This one is instruction memory, and second memory, right, data memory. Okay, then you should have one more connection right here, okay, like this, address and data. Okay, so two options, right? Either this or that. Okay. Okay, let's move on. Data hazard problem. Okay, this one. Kashmop?
Data is not ready for the subsequent dependent instruction.
Okay, thanks. Data hazard is also a very simple problem. Okay, so data hazard is coming from data dependence. Okay, what do you mean by data dependence? Take a look at this. Take a look at this simple code snippet. You have addition instruction and second instruction, subtraction instruction. I color coded S0 register here. First instruction, S0 is destination. So addition instruction is updating S0, essentially producing S0 register by adding these two. And second instruction is consuming, right? Is using that output S0, S0. Data dependence. Okay. The problem is, take a look at this pipeline execution diagram. So patch to execute. First instruction, you have to go through these five different stages, right? Patch, decoding, execution, and write back. Okay. And the problem is S0 register is updated in the last pipeline stage, which is write back stage. Okay, but second instruction need S0 register in decoding stage, which is 2 clock cycles before. Two clock cycles, before this write back happens. Right? 2 clock cycles. 2 clock cycles before you need, right? You need future data. Okay, this is a present decoding, right? But you need future data. So you cannot pass this future data to present. That is a problem. And how to resolve this problem? Simple solution is you insert this bubble. So what do you mean by this insert bubble? You stop decoding stage, 2 clock cycles. Okay, stop here, decoding, then execution. So that means after updating register file, right? After updating S0 register, you are reading S0. Remember the convention? Shade on the left, write operation. Okay, and shade on the right, read operation. So after, okay, write back stage. So write back stage, and time, and we have clock. Clock is running like this. So update operation, right? Update, shade on the left, right? And read operation, write operation. In other words, write operation and read operation. Shade on the right, right? Shade on the right, read operation. So after you update register file, then read, right? So this is a simple solution, but we don't like this solution. Why? Because performance, right? So if you stop the pipeline 2 clock cycles, then essentially you are not doing anything useful for these 2 clock cycles, just to stop, right? So we don't like that solution because performance is not good. Okay, we want to finish one instruction in each clock cycle. Remember, this clock cycle we want to finish this instruction. Next clock cycle we want to finish subtraction instruction, and so on. But if you look at this pipeline execution diagram, this clock cycle addition is done. But to finish second instruction, you need 1, 2, 3 clock cycles. So we don't like that solution, right? Because performance, penalized. Okay, performance is not good. So the better solution is forwarding, instruction forwarding. So what is forwarding? Very simple. That is previous the slide, right? Pipeline execution diagram. You are stalling decoding stage for 2 clock cycles. Then the thing is, why do you have to stop decoding stage for 2 clock cycles, given that this data, right? T0 plus T1, data is ready. When the data is ready, addition output. What do you think? Addition output is available after execution stage, right? After ALU operation, addition output is ready. Why do you want to wait until, write back, write back stage, right? Write back stage update, register file. Right? You don't want to wait, right? So solution is forwarding, right? Remove that. I don't want to, stop the pipeline, just to use that ALU output to ALU input. Forwarding, right? Forwarding. So don't be confused. We have only one. Pipeline, right? So if I draw ALU, then execution diagram looks like this. We want to use ALU output. Okay, we want to use ALU output to somehow that input. That is the one, right? That is the one, right? Or sometimes your source operand, right? OP1, OP2. First source, second source. Sometimes you need, right? Here. Depending on instruction sequence, right? Depending. Assume that you have S0 and S0. Here, S0, second source operand is also S0. Then you have to do this, right? You have to create that path, right? Does it make sense? But this one is not the full solution, right? You have some flip-flop inserted somewhere, right? Like this. Flip-flop. You need some flip-flop, right? A, T, and Q. That will complicate hardware design because you are new to hardware. Right? The flip-flop. Flip-flop is dividing stage, execution stage, and then memory access stage, mem stage, execution stage, right? So let's the concept first, right? Concept first, and we will get into the detail. Okay, second problem. Okay, data forwarding problem. This one, simple forwarding. Simple forwarding is not fixing, all different cases. Think about this instruction sequence. First one is memory access instruction. Okay, which is updating S0 register. And second instruction is consuming, right? Consuming that S0 register. And if you draw pipeline execution diagram, it looks like this, right? Think about first instruction, memory access instruction. The data is available when the data is available. The data you read from memory. Data will be available after memory access stage, right? But you need this data, even though you apply forwarding technique, right? The data should be available before ALU operation. That means this. Same problem, right? So you are here present and you need future data. Okay. So you cannot, forward, you cannot use future data in present time, right? Now, right? Future data. So what do you have to do? The simple forwarding, right? Simple forwarding cannot fix that problem. So in this case, you don't have any choice. You have to stop the pipeline for 1 clock cycle. Stop decoding stage. Here, decoding stage, bubble means another decoding stage. So to decoding stage, stop decoding stage. Okay. Then in execution, you are feeding this data to ALU input, forwarding by using forwarding. That is called hardware interlock. Hardware interlock. Hardware interlock means you stop the pipeline. Okay, hardware interlock. So this one is called load use case. Load, right? Load data. Data from memory is being used by next instruction. Load instruction, right? Load instruction. And next instruction is using that output. Load use case. And then this bubble, so if you design CPU, you have to implement, you have to design this hardware interlock mechanism, because if the instruction sequence is this LW and next instruction is consuming, then you have to stop. So you have to implement that hardware interlock logic, right? But somehow sometimes you can fix this problem. You don't want to stop. If you don't want to stop pipeline, then you can get help from compiler, from software. Hardware should always provide this hardware interlock. But if software is helping you, then you don't have to use this hardware interlock mechanism. You see the point? Hardware should always provide that mechanism. But if software is helping you, then this function is not used. What do you mean by that? This one, Seungmin, can you please?
Code scheduling to avoid stalls. Reorder code to avoid use of load result in the next instruction.
Okay, thanks. Think about this simple C code, right? A is equal to B plus E, C equal to B plus F. Okay, you want to execute this, two statement, C statement, and compiler will generate, instruction sequence, right? And assume that compiler gave you this code. Okay, and we have the first instruction is what? We assume B, T1, E, T2, F, T4, right? So first instruction is loading B into T1 register, and second instruction is loading E, right? E into T2 register, and then next instruction is doing addition. First addition B plus E. Then you have to update this memory location, right? Local variable A. So store word instruction. And then second statement, B is already in T1 register. So you need to load only F, right? Which is in T4, okay, LW. Okay. Then addition operation, B plus F. Addition. Okay. T1, which is B, T4, F. So B plus F. So T5. Then you have to update that local variable which is in memory, right? See, so store word instruction. So if compiler gave you this one, this is not good code because that will create hardware interlock. You have to use hardware interlock, right? T2, data dependence, load use case, right? Load use. But compiler is smart. Compiler understand this load use case. Maybe, then compiler give you this one. Same function, but different mix of instructions, right? So the thing is, the key point is you want to insert one instruction, some independent instruction between these two. LW and add, you want to insert some unrelated, independent instruction like this one. So actually this one is one. This one LW, that instruction got inserted in here. So if you insert that instruction between these two, you don't have to use hardware interlock, design. But design is always there inside the CPU, right? In case compiler, provide this, sequence. But okay, better not to use, okay, if possible, right? So if you count number of clock cycles for execution, first LW instruction. LW, we start from patch, decoding, execution, memory access, write back. First instruction. Next LW instruction. Patch, decoding, execution, memory access, write back. So count number 1, 2, 3, 4, 5, 6. Then addition instruction, right? Patch, decoding, execution, memory access, write back. But you have to store the pipeline. How do you interlock? So not here write back, right? Probably 7, 8. Okay. So should be like this. Decoding, stop the pipeline, right? And execution, memory access, write back 2 clock cycles. So if you store 1 clock cycle, 2 clock cycles for this instruction execution, right? So if you count 1, 2, 3, 4, 5 for this one, right? So here, let me count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 for first instruction, 6, 7, 8, store, right? 7, 8, 9, 10, 11, 12, store, right? And 13 clock cycles to execute that code. But if you insert that instruction, let's count 1, 2, 3, 4, 5 for first instruction, 6, 7, 8, 9, 10, 11. 1 clock cycle each, so 11 clock cycles. So if compiler helps you, then the performance is better, right? So it is the collaboration between hardware and software, right? Hardware alone is not providing good performance. You need help from software people, right? Compiler, right? So collaboration between hardware and software. Bottom line is the hardware interlock logic is always there. You have to provide that design in case you have this instruction stream. This logic should be there all the time. Otherwise, this code is not running, correct, right? This insertion. Okay, that is about data hazard problem. And next one is about control hazard problem. Okay, so that will be the fifth milestone, the problem. Okay, so let's just stop. Let's just stop here. Then where is that? Pipeline number 2. Where is that? Oh, here. Okay. Let's talk in detail, some more detail about data hazard. So I explained the concept, right? Some principle. Then we need to get into the detail, right? How to implement pipelining, also how to fix, how to resolve, and how to detect data hazard, and how to resolve that problem, right? So we have to talk about some detail. Fourth milestone. So before, okay, what is it? Number 2. Okay. Okay, before that, okay, so that is the pipeline data path, focusing on the data path. Okay, you insert a flip-flop. This bar means flip-flop, right? So cut the line and flip-flop. This cut the line and flip-flop, right? Cut this line, flip-flop, 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 all flip-flops, many different flip-flops. Okay, so if you create a pipeline, let's execute some instructions, right? And if you are able to take a snapshot of a computer CPU at some point, then snapshot would be looking like this. Okay, snapshot. So in write back stage, CPU is updating extend register. Okay, extend register. In memory access stage, subtraction instruction in memory access stage, and you don't have to do anything. Nothing is done because subtraction is not accessing memory, right? You are just passing, right? Subtraction is not, instruction is not doing anything. Okay, but anyway, that is in memory access stage. And execution stage, ALU is doing addition. ALU is doing addition, okay, of X3 and X4. And decoding stage, register file is providing source operand X1. Okay, reading, and also this immediate is created, okay, with sign extension, 32-bit immediate, source operand preparation. Okay, and patch stage, you are reading new instruction, which happens to be addition instruction. That means, look at this, CPU is executing these 5 different instructions at the same time. That is the beauty of using pipelining, right? So these 5 different hardware resources are being utilized at the same time, right? That is the beauty. Let's execute some instruction. First clock cycle, assume that you are executing LW instruction, memory access. So first stage, instruction patch, right? So you are reading from instruction memory, right? So remember the convention, shade on the left. Shade on the left means update operation. Updating what? Let me draw. You have instruction memory, right? Patch stage. And then that vertical bar means flip-flop, right? Flip-flop. Clock, ENQ 32-bit. Input and output 32-bit. So that is stage. You're dividing stage, right? So patch stage and decoding stage. Okay. So you read a new instruction which happens to be LW, and then shade on the left. Okay, we use the convention. Shade on the left means you are updating, you are storing actually, storing here. You are at the rising edge. Let me draw here. Clock. Okay. So at the rising edge of the clock, okay, that clock, this clock. At the rising edge of the clock, you are taking a picture of this input to this Q output. Okay, so you are taking this guy, camera, right? Taking picture when this rising edge of the clock, input to output, the rising edge. So you are storing, right? Storing at the rising edge. So that convention, right? Shade on the left. This one is called. This one is called. This one is flip-flop, right? Flip-flop. And we use this terminology, pipeline register. This one, pipeline register. This one. this register. This register is not visible to software people, right? Software people cannot see this. It is only hardware, right? So we register file, right? We have register file in decoding stage, right? X02, X31. This one is visible. Software people can see X02, X31 registers, right? This is software visible registers. But this one, pure hardware pipeline register, it is not visible to software people, right? Software people cannot see, cannot program, cannot do anything, cannot do anything with this one. Pure hardware, right? So the convention, shade on the left, patch stage, and then next clock cycle, right? Decoding stage, shade on the right. You are reading, right? You are just reading, right? Reading from, okay. This flip-flop pipeline register. Provide RS1, okay, T1, right? RS1 number, and then reading from register file. Shade on the right, read operation. Okay, then sign extension logic, full use, right? That is fully utilized to do sign extension of this 8, right? And at the rising, okay, at the rising edge of the clock, you have here flip-flop, right? Clock is common, right? You are supplying same clock and D and Q, and we have here register file, and providing first source operand, OP1. Okay. For sign extension logic, same thing, right? It is very crowded, so let me. So you have sign extension logic, right? Logic is taking some immediate from instruction. Okay, immediate, 12-bit immediate, and then 32-bit output. That is also stored in pipeline register. So clock, same clock, right? Same clock, same clock, same clock source. Okay, so like this. Sign extension logic, flip-flop, right? Flip-flop. Here flip-flop, flip-flop. Okay, decoding stage. Next clock cycle, same thing, right? Execution stage. In execution stage, you are doing addition T1 plus 8. Okay, and generate memory location. This one, this bold line. Same thing. We have flip-flop, right? Pipeline register. Okay, shade on the left. You are storing at the rising edge of the clock, right? And then fourth clock cycle. 1, 2, 3, 4. Fourth clock cycle. You are reading from data memory, right? You are reading from memory, and then that data will be stored in pipeline register at the rising edge of the clock. And then fifth clock cycle number 5, that will be updated to register file. Okay. So actually, to update, if you have a good eyes, then probably you have spotted some problem with this data path. Here you are providing data, right? Data from memory. Okay, this one, and the location information S0, right? Destination location information is coming from that pipeline register, which is in decoding stage. Okay? So we have some problem, right? Decoding stage. That happened, 3 cycles before, right? So that means you are updating. Okay. So let me decoding stage, right? Decoding stage, it is not scale, right? So we have execution, memory access stage, MEM, and write back stage, right? So you are updating data in write back stage, right? Data is okay, but location information, register file destination, that is generated in decoding stage. You are trying to use that one. Then that means you have to pass that destination register number to here, pass, right? Pass, right? Using flip-flop. So like this. So follow this orange line. That is destination register number. You have to pass that destination register number to execution stage. Okay, then execution to mem stage, mem to write back stage. So in clock cycle number 5, you are providing both data and location. Same time, right? Time, right? Time. Clock cycle number 5. Clock cycle number 5. Okay. In write back stage, you have to provide data, right? Data to register file, right? Data to this data to register file, and location to RD, right? RD. Location, right? So when you create data path, pipeline data path, you have to be careful, right? So inserting flip-flops, okay? Not only this actual 32-bit data, but also this register number, okay? Okay. Stored, if you execute stored instruction, everything is the same. Okay, patch, decoding, execution, everything is the same as LW instruction, memory read instruction, except in memory access stage, you are updating this one. You are updating memory, right? You're updating. And then what do you have to do in write back stage? So stored instruction, patch, decoding, execution, mem, write back. There's nothing to do, right? Write back stage, you don't have to do anything, nothing to do in write back stage. This instruction is not updating register file. It is updating only memory, right? Memory. So you don't have to do anything, right? Okay, so okay, in this PowerPoint, we are assuming because now we have, so this is a data path, almost a data path only, right? So ALU input, output, so no control information, right? No control information. So if you add control information, it looks like this. Register write control signal, ALU source, remember? Which source you want to pass to ALU? Data from register file or sign extended immediate ALU source. And ALU control, what kind of operation you want to do? ALU, right? And zero, right? Zero, flag output from ALU. Branch instruction, BEQ, for example, right? And memory write control signal. Here I specified mem read control signal. So, okay, and this one, mux selection, which data you want to pass to register file? Data from memory or follow the second input. This one. Data from ALU, right? ALU output is passed to mem stage, then that is also passed to write back stage. So this mux select this one or ALU output. Okay, so we have mem to rec control signal. Here, remember that, for explanation purpose, I put the branch, okay, the branch control signal here. The thing is, all control signals, all these control signals, regulate, AL source, all control signals are generated in decoding stage. Remember, we have control unit in decoding stage, right? And that is generating all different control signals. And some control signals are consumed in MEM stage, like AL control, AL source. Those two are consumed in execution stage. Okay. And these three, branch, MEM, write, MEM read, these are consumed in memory access stage. And MEM2 write and write back, reg write, right? This one and reg write, these two are consumed in write back stage. Okay, you have to separate generation, what stage those control signals are generated, and what stage you need that control signal, right? Everything is generated in decoding stage, right? But some are consumed in execution, some MEM, some in write back. Okay, so like this. There is also one confusing point, right? So in execution stage, in our example, right? This is example. You don't have to follow this example explanation purpose, right? These two control signals, right? AL source, AL control. These are consumed, need in execution stage, and these three are consumed in MEM stage. These two in write-back stage. Okay. So that means, what? Important, right? These control signals also should be passed through pipeline register. Not only data, right? Not only data you pass, but control signal should be passed to next stage, right? Data and control signal, right? Data and control signal, right? So here, execution stage, 2 control signals. MEM stage, 3 control signals consumed. Write back, 2 control signals. Depending on instruction types, right? Depending on types, that can be determined. AL source, R type, 0. Meaning you want to use data from register file. R type, right? Addition instruction. Branch? No, it's not branch, right? Addition, think about addition instruction. Mem read? No, right? You don't have to read memory. Mem write? 0. And so on, right? We went through that, example, right? So then, complete pipelined CPU structure looks like this. Okay, so here, control signal. Control signal is generating all different control signals that is passed to next stage. Okay, so here, right? That is flip-flops, right? Flip-flops. Here, flip-flops, flip-flops. Same thing, flip-flops, flip-flops, flip-flops. Okay, so here, that control signal follow this line, orange. AL control. Okay, and this thin orange line, that is ALU source. Okay, so in our example, we have a 5-bit control signal, AL control, and 1-bit ALU source. And these 5 each 1-bit, branch 1-bit, memory 1-bit, 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 1-bit. Okay, so here, okay, 5-bit and 1-bit. Okay, this thin, okay, this thick orange, and some control signal, right? That branch, mem write, memory, these 3 are consumed in memory access stage. That means these 3 control signals should go through 2 different flip-flops. Here, first one, to pass that guy into execution. And then next flip-flop to pass that guy to mem stage. Then finally consumed here. Okay. When it comes to these two, mem to reg and write back, these two should be going through 3 pipeline registers from here. Okay, 1, 2, and 3. Okay. So example is give me 2 minutes. Okay. So let's assume you are executing LW. Instruction is LW. Then decoding stage. A control unit is generating all different control signals, and also data pass, right? Control and data pass, right? It is register file is providing what source operand x1 and 9 sign extension, and at this time, it is clock cycle, right? Instruction patch unit is reading new instruction, which happens to be subtraction. And next clock cycle number 3. Okay, this one is moving. Decoding instruction in decoding stage is moving to execution, and that guy instruction in subtraction is moving to here like this. And next clock cycle, same thing, right? One moving like this, right? Like this. LW is moving. Okay, subtraction is moving. Patch is patching new instruction. Clock cycle number 5. That guy is moving mem to here, subtraction to here like this. Okay, let's go back. Clock cycle number 2 here. Clock cycle number 2. It is generating this control signal, right? So 5-bit ALU control and 1 bit. Okay, so clock cycle number 3. Then look at this. 5 zeros and 1. Okay, so 5 zeros and 1. According to our encoding, 5 zeros means addition operation. You are asking ALU to do addition, because you need to do x1 plus 9, right? Addition operation. And then 1 is what? Follow this line. 1 means you want to select second input, which is sign extended immediate. Okay, that immediate 9. Okay, and then mem stage, right? 0, 1, 0. Okay, if you go back, control unit generated 0, 1, 0 for that branch mem write, mem read. 0, 1, 0, right? 0, 1, 0. 0. No. 0. If you follow this line, 0. Okay, 1 means this one, mem read. 0, 1 and mem write is 0. So 0, 1, 0. So next clock cycle number 4. 0, 1, 0. 0, 1, 0. 1 means memory read operation. So try to follow this one. This is not that hard to follow. On Wednesday's class, we will talk about detail how to implement, how to design digital logic to resolve data hazard. This slide actually, right? That branch data hazard detection. You need to detect, right? Okay, there's a data hazard. Then you can solve that problem, right? Detection, then solution. Okay, that logic. We'll talk in detail about that on Wednesday. Okay, But because you have to do first milestone, I strongly encourage you to take a look this design first. Try to understand yourself first. Then Wednesday's class will be easy to follow, I guess. Okay, that's it for today. Anything you want to ask? Again, first milestone is taking time, right? Some student never sleep for 1 week. Okay, please, start as soon as you can, right? So, don't wait until the last minute. It will definitely takes time. That is for sure. Okay, I guarantee. So don't wait. Okay, don't wait. Try this and that and run simulation. Okay, run other simulation. Try to check the function of your implementation, right? Debug, right? Okay, that's it for today. I'll see you on Wednesday. Bye. Okay, thanks.